All right. Okay, so we have today. What I want to do is I want to talk about chapter 4. Now, I had a lecture from 8 to 9, and I apologize for not having one 9 to 10 last week. I just couldn't do it. Hopefully, you guys had a chance to review the lecture I recorded from 8 to 9. Uh, for this week, I'm doing a little different. The lecture I had from 8 to 9, I covered a problem, force couple system, and I decided to I'm gonna not do that problem now because I ended up running out of time and not being able to do a chapter 4 3D problem that I wanted to do. So that way, if you want to see that force couple problem, you can just look at the beginning of this week's lecture after I post it on Canvas. So we're going to jump right into week 4. So you guys pretty much have finished chapter 3. So as far as the quiz, I'm not positive on the subject, but I will send you guys out an announcement today to let you know what it is. And the other thing is, if you probably saw what I sent out a sheet with an announcement yesterday that has the figures that I cover in this lecture, which I thought might help you guys out so that you actually have it in front of you. And I also mentioned in that I won't be available on Tuesday. I have to be out of town, so I won't have office hours, but I will make those up on Wednesday when I normally don't have them. So I'll announce the time for that. So you guys can definitely have the same number of hours this week as normal. As far as next Wednesday, we have our exam. So basically 9 days from now. And so I would, it's never too soon to start studying. I'm realistic. I know you're not going to study now, but I wouldn't wait until next Monday to start studying. Reason being is next Monday, what we're going to do is we're going to have this lecture will be a review session for the exam. And I will go over everything we've talked about up to end of chapter 4, and that's what will be covered on the exam. And then it'll be some open time for you guys to ask questions. And so I would, the best use of that time is if you can figure out the few things you don't understand and make sure you do by the end of that, because the test is going to come before you know it. So first thing I want to do this morning is talk a little about the quiz. And so the quiz was, let's go ahead. So looking at the quiz, you have basically I gave you a line with two forces. So very similar to what you've done in homework. The only difference here was you had two forces about the line. For the most part, and I have these almost graded, so I will hopefully post them later today along with the solution and your answers. But for the most part, not many people got the actual answer correct, but a lot of you got the process correct, which is more important to me than if a few of you made math errors at the end, subtracted rather than added, or you had your R vectors reversed. So you had the signs reversed, which of course is going to screw everything up in the answer. But the point is that in a problem like this, you always, the things that are really important to understand is that this moment about the line is a scalar value, and the lambda, the dot product, the lambda is always the unit vector of the line. So I saw some different variations. I saw people dot producting the unit vector with the force. I saw the R vector being a unit vector. So make sure you're clear on what's what in that, because that's going to, and it's always the same. You're always going to have the unit vector of the line dotted with an R vector, which is any point on the line to any point on the force crossed with the force. So the other mistake I saw in this one was the actual breaking up of the 500 Newton force. So from looking at this, you can see that 300 Newtons in the Z is going to be your Z component of that. And then 400 Newtons is going to be your horizontal projection. So then you have 3/5 of 400 and 4/5 of 400 are going to be your y and x respectively. So x and y respectively. So 3/5 of 400 negative direction is x. 4/5 of 400 is going to be your y direction. Now I will post the solution, and so you can look at it because I know I'm going through it pretty quickly. Your a relative to e vectors are what I got: -2, 2, 2, and 0, 2, 2. Remember, r is never a unit vector. And then the unit vector for the line EC, not CE, but EC, is as I've shown. So the final answer is about 21.8 plus or minus 1, depending on how you rounded your answers. And so that's the quiz. Any questions about the quiz? Anything that doesn't make sense? Okay, well, good. So the next thing we went through with chapter 3. So chapter 3, for the exam, you want to make sure you understand all the main topics. So you had moments about a point, moments about a line, then you had the force couple system, then you had the equivalent couples, and then you had the equivalent system. So you had an example of all those types of problems on your last homework assignment. So you should be in good shape if you understand the homework. But again, if you have more questions, please ask. This was the problem that I was talking about. I'm not going to go through it for the sake of time's sake. It's on the other lecture. But this is just a simple force couple system. It's just a little more complicated because you take your 9.8 pound force, you convert it to a vector, and then you cross it with O relative to D. That's probably the easiest, R vector. And then, or you could make a point down here at the on the XY plane. But you do that gives you one moment. And then of course the 9.8 and IJK is the other one. And the only other thing you have to add in is you have to take this 52 foot-pound moment and make that into a IJK. So, and you can do that easily by taking the unit vector of this force and multiply it by the 52. Anyway, you'll add the moments together. Remember that anytime you have a moment acting on an object, it's a free moment. So even though it's spinning around there, it's actually trying to spin the entire object around. So its location isn't critical to where it's at. That didn't make any sense. Its location doesn't affect its effect on the object. So that's what I meant to say. Now, again, this is for a rigid object. This assumes the material has no yield point. So in our universe, all our materials have an infinite modulus. Okay, so let's go on. Let's talk about week 4 in chapter 4. Now, most of you find chapter 4 to be a little easier than chapter 3. I think it's a little more straightforward. It's more staticky because everything's set equal to 0, unlike chapter 3. And so the important part that you need to recognize is the free body diagram. Doing good free body diagrams is probably the most important part of statics that you take away, because that's going to carry through to you when you go to dynamics, C204, and subsequent classes. And if you're a lucky ME to take intermediate dynamics, then it'll come back too. And you'd actually be surprised if you're ME, and probably some of the other majors, but when you get to your 400 level design classes, you'll revisit statics. And first thing, and I've heard feedback from some of the instructors that teach that will say that some of you guys have forgotten how to do good free body diagrams. So don't make me look bad. So, yeah, this is it. It'll help you. So the thing with the free body diagram is you don't have to put all the dimensions on it, and that's the important thing is draw it and make sure that you have all the forces. And we're going to practice that, and you'll also practice that at homework. All right. So let's look at this first example. This is a simple 2D problem, and you have this uniform smooth rod subjected to a force and a moment is shown. So determine the reaction. So you have these wheels at C and the wheels at B, and then the smooth meaning there's no friction. and it's resting it up against the wall A, and it has this 300 Newton force vertical at this end. So I want you to take a minute and draw what you think the free body diagram should look like for this. Okay, so I know may not be done, but this should look kind of like what you're getting. Don't ignore the axis up here. It's not necessary to tilt the axis. That's just the picture. So if we think about this, we don't have to call it prime. It can just be C and B. So that's how we'll solve it. But what you probably found is you drew the rod. You have the 300 newtons going down. You want to label angles because those are respected to the forces. You have the CY, the BY, and you have the 30 degrees. And then you have the 4,000 Newton meters. Now, whether you get the 2, 4, and 2, that's not critical to your free body. And in fact, if you can put it in, doesn't make it unreadable, then do it. But a lot of times the dimensions will clutter it up and make it confusing. So I would say is that the main thing is just to get the forces. That's critical to it. If you can get the dimensions, that's okay, but it's not required. So how are we going to solve this? No, we have, as you see, we have C, B, and A as our unknowns. So if we look at that, here's my, now I think if I want to make sure that you should be able to get, if I do this, then, actually, sorry. There you go. Make sure this is showing when I record full screen. So, let's just do this. There we go. All right, so here's our drawing of what we have. And so when we solve, we have C, and we'll call it just CY, and we'll call it BY. The Y doesn't matter. We have AX, all right? And so we'll just stay with our standard X, Y axis, all right? Now, in some cases, it helps to tilt the axis. And this one, I'm not necessarily sure it is. So I'm just going to solve it the way it is, the way it's in this orientation. And so you have your lines up here. And the reason is you have rollers on both sides. But if you think about it realistically, it's only going to touch one roller on either side. Now, mechanically, if you think about it, if my pencil were this rod, it's being pulled, you have a 4,000 Newton meter moment wanting to twist it like this, right? So it's wanting to do this. So it makes sense that if it's wanting to do this, it's going to hit CY. It's going to be pushing off that reaction. But more likely than not, it's going to want to hit, the reaction at B is going to be on this side, right? It's going to want to do this. And so I've drawn BY that way, and that's fine. And when I do the calculations, it'll tell me whether I was correct or not. But I should get a negative for BY because mechanically this should do this. So let's see what happens. So when solving a problem like this, first thing is we know that we have, it's 2 dimensions. So we have 3 equations. We can sum the forces in the X to 0. We can sum the forces in the Y to 0 and sum the moments to 0. All right, and that's usually about a single point. But we can't have like 3 moment equations. That won't help us to like sum the moments about 3 different points. So we really just have these 3 to work with. So if we take, for example, the X, let's just look at the X, sum of the forces in the X. So if we do that, what do we have? We have CY sine 30, right? Because we have this little part of this going that way and that going that way. Same with BY, that little bit going that way. And so CY sine 30 plus BY sine 30 minus AX equals 0. And so if we simplify this, this really comes down to be CY plus BY equals 2AX. All right. So we have that. So then we do the same thing, sum the forces in the Y to 0. And this is pretty much the way you're going to solve all these problems in chapter 4, is you're going to first draw your free body diagram, and then you're going to set up an equation, sum the force in the X, sum the force in the Y. Now, in what order you do it doesn't matter, because in some cases you may have to, solve, usually the moment equation is what's going to solve for an actual number, and then you're going to go back and plug that into these subsequent equations to get your final answers. So now if we sum the forces in the Y, what do we get? Well, we know it's minus 300, and then it's going to be plus CY cosine 30 plus BY cosine 30. And that equals 0. So if we solve for that, we get CY plus BY equals 200 times the square root of 30. And that 200 is about equal to 346.4. All right. So 1, 2, 3 unknowns, 1, 2 unknowns. So our third equation, now we're going to sum the moments. Okay. So this is where you pick a point. And I always say is pick a point that has the most unknowns. That generally works the best. Now, no point has the most unknowns, but if we sum the moments about the point A, then what that's going to do is that's going to eliminate A as an unknown, and it's going to leave us with just CY and BY. Well, we have this equation with just CY and BY, so that means we're going to have 2 equations, 2 unknowns, that we can solve. So if I do that, I'm going to go ahead and say sum the moments about A to 0. And what am I going to get for that? I'm going to have, first 4,000 Newton meters, right? Because that's a positive moment. And then I'm going to have plus 300 cosine 30 degrees. And the distance is 8 meters from A. And then that's going to be minus BY times 2 minus CY times 6. And that'll equal 0. I'm sorry, it's getting kind of messy. So we have the moment, right, from up here. We have the 300 newtons So I'm only interested in this leg of the 300 newtons because the other leg goes right through A, right? So I have that, and then I have this, and they're wanting to push it around in a clockwise position. So therefore they're negative. These two are positive. So if I simplify this, I get 6cy plus 2by equals 6,078. All right. So what I'm going to do now is I'm going to bring this equation down here and multiply it by -2. So if I do that, I get -2cy minus 2by equals -400√3, right? And so add them, and I end up with 4cy equals 5,385. So the rest is just algebra at this point, because now I'm just going to substitute back in. But I end up with cy equals 1346. And notice now, if I plug that back in up here, I get, if I take this equation, I get 1346 plus by equals 200 square root of 3, right? And this is about 346. So by ends up being a -1000, which is what we thought it should be, right? We thought it should be negative, and the math shows it because this reaction up here should be on this side. It should be a negative, okay? And then if we plug in these values up here, we can get our AX value. And AX ends up being, if we do it, we end up with AX equal to 173.2 newtons. All right. And those are our three reactions. Any questions on this problem? Make sense? Good. So 2D ones aren't too tough. They're not too time consuming. They usually go, and like I said, is as long as you a lot of the chapter 4 problems you follow a recipe on, and unlike other classes that you're in where each problem is a lot different, a lot of these are very similar. So it's kind of a reprieve. But so let's look at what happens when we go to 3D. Now, before we talk about 3D, though, I want to mention that in 3 dimensions, you have something we haven't really talked about, are reactions. And so when you think about reactions, you think of, how does something, say, anchored to the outside world? So, for example, if we have, in this last example, we saw that AX was just, you had this like that, and then AX was just pointing that way, and it just had a single force pointing that way because it was just resting against a wall. But in other cases, it could be more complicated. So you take the most complicated would be if in 3D, if you were to take, say you had a pole like this, and let's say it's embedded in the ground, then in this case, if this is your X and then Y and then Z up here, then if it's embedded, you're going to have a moment about the X, a moment about the Y, a moment about the Z. You're going to have a reaction force in the Z, a reaction force in the Y, and you're going to have a reaction force in the X. So you have 6 unknowns in this case. So that's the most that you'll see. Or most of the time you'll see something like this. It's called a ball and socket joint. It'll look something like this, where you have, it's connected by ball and socket, in which case, if this were in 3D, you'd have just a force that way, a force that way, and a force that way. So 3 forces, but can't support a moment because it's free to rotate. So equivalents to these would be like in 2D, you might have something where you have something pinned to a wall, in which case it's free to rotate. So it'll have, reaction like this and like this. But if this was then subsequently embedded in the wall, then it's going to have a moment. And then, of course, it's going to have force. So it's going to have 3. So there is a diagram in your book that shows different reactions, and I also have a better one that I post of reaction types. And I don't expect you to memorize them, but you'll, on the test, it's open notes, so you'll have a sheet of reactions that you can look at, and this will help you discern, what type of problem, when you're looking at it, what you have to know. So obviously, solving a problem like this is going to be a little different than one like this, because you're going to have to account for these free moments that are acting in these 3 axes, whereas here you don't have anything to worry about. We tend not to do too much like this. It gets really complicated. Most of the time we have something like this, but we'll attack it as we see it. Now we have about 20 minutes. This will give us time to go through that last problem, which I wanted to do in the earlier lecture. And that's this one. So as I said, in 3D equilibrium, there's kind of a way to go. First, you're going to draw the free body diagram, identify your force vectors, known and unknown. Then you take a moment about the point with the most unknowns, solve for the unknown tensions, sum forces to solve for unknown reactions. So those 5 steps are pretty much the recipe for solving these, and we're going to see that in every problem we do. So here's an example. So we have this pole that's sticking out of the wall, and you have this figure. I uploaded it to you guys yesterday, and it's also on Canvas. And you have the tension AD, so you have a rope AD, and you have a rope CE going up to those points, and then they're connected at the points respectively. And then you have this 8,000-pound load at B. And what we want to determine is, what is the tension in AD, what is the tension in CE, and what is the reaction at O. All right, so that's what we're looking for. Now, if we look at the free body diagram, here's my free body diagram for it. So here's the drawing, the original drawing here, and then here's my free body diagram. So what I've done, I have the force OZ, OX, and OY. There's no moment because it's a ball and socket. I have tension AD and tension CE. These are both scalars. I have P, the load 8,000, and that's it. So that's where I start. So first I have my free body diagram. This is what I want. So then how do I solve it? So the first thing is we want to know is, what are the tension vectors? Okay. So just like we did in chapter 2, we know that tension AD is equal to lambda AD times the scalar AD, right? So if knowing that, we can go ahead and calculate it. Now I know you guys know how to do that, so I'm just going to write these down. So I know that tension AD is equal to 0.5077 I AD. Sorry, I should put the I. Redo that. So 0.477 I minus 0.6093 J plus 0.6093 K, all times tension AD. And then the other one, tension CE, is similar, and it's negative 0.4626. And you don't have to carry all these decimals. I just did. 7930J plus 0.3965K, tension CE. All right, so those are those. So, and then now I've shown you those first, but really how do we solve this? Remember what we said is first we figure out what these are, and then we want to take the moment about the point with the most unknown. So our governing equation for this is going to be sum the moment about O to 0. And that's really going to be R A relative to O crossed with TAD plus R B relative to O crossed with P plus R C relative to O crossed with TCE. And all that equals 0. And so that's the big difference about what we haven't done before is, so effectively we're setting up a matrix RA, that cross that plus that cross that plus that cross that all equals 0. And this is like every time you do it, you do the same thing. I mean, it's the same as what we did in 2D, right? First we found out, we didn't have to do this part, but we summed the moments, but we first summed the moments about the point with the most unknowns. Only, we didn't have to do cross products because it was a simpler moment. So if we're going to do this, we have that equation, we have these, and then of course we're going to need our R vectors. So in this case, our R vectors are easy because we're just going from here out to this point, here to that point, and here out to this point. So they're just in a single dimension. So R A relative to O gives us 3J, and R B relative to O gives us 5J, and R C relative to O equals 6J. And so then it's just a question of setting them up, right? You just set them up as cross products. So if I do that, let me go ahead and write them out. So I have RA relative to O, tension AD, and what do I have? 0, 3, 0, and 0.5077 TAD, negative 0.6093 TAD, and 6093 TAD. That's why I like fractions better instead of these, but all right. So there's the first one, and then R B relative to O. Sorry, getting kind of tilted here. Do this. There. And then that's going to be just P. So this one's easy. It's just 0, 5, 0, and then 0, 0, negative 8,000. All right, so plus this, plus, and then R C relative to O, and then tension CE. And so negative 0, 4, 6. Let's see what those were. 7390. I know you can't see the screen. I'm going to put it up again. So my chicken scratches are negative 4676 CE, 0.7930 TCE, and then positive 0.3965 TCE, and then you have basically 0, 6, 0. All right, so it's kind of a little sloppy, but I'm writing it quickly. So as you can see, when I take my time and write it, it looks much better. So this is the kind of drawings I would like to see on your homework, some that take the time to do it. I know that if you're writing quickly on a quiz, it's not going to look great, but when you have your homework, you have the time to make it look good. So please do. So anyway, we have all this. We know that all equals 0. And I know you guys can figure out all the cross products. So we know just like what we did in chapter 2, you now you do all your cross products and you basically separate them into IJK. So you figure it out. So you have an I equation. And in this case, we end up with 1.828 TAD plus 2.379 TCE, tension CE, minus 40,000 equals 0. So we take all the components in the I, put those down, and then for the K, we ended up with negative 1.523 tension AD plus 2.776 tension CE, that equals 0. So 2 equations, 2 unknowns, we solve, we end up with tension AD gives us 12,770 pounds, and tension CE gives us 7,010 pounds. All right. So, or correct sig figs would be 12.77 kip and 7.01 kip. All right. So we're not done yet. So that gives us, now we just have our tensions, right? That's part of it. And then the last part is to go back and figure out what are the reaction at O, right? So we have to go back now and see, what is this? Well, that's easy because we can go ahead and break, now that we know the force vectors, we can break them up into their IJK and we know how much force is in each direction. And then we just set up our equations where we sum forces. So we take this and we say, well, we know if we sum the forces in the X to 0, we know that we have OX, which is our unknown, and that's going to be plus 0.5077 tension AD minus 0.4626 tension CE, and that equals 0. So we can plug in our respective values for AD and CE and solve for OX. So it turns out that OX, it gives us a negative 3,240 pounds. All right. So that makes sense because there's more pulling in one direction. So that means X is just pulling in the negative X direction. And then we do the same thing, sum of the forces in the Y to 0, and we get OY. And then that's going to be minus 0.6093 tension AD. And again, I'm just taking the coefficients directly from the original equations, right? I'm taking them from here, right? So when I say the Y, I'm taking 6093 and 7930, just like I took 5077 and 4626 and here. So I get that 6093 minus 0.7930 TCE equals 0. And then that gives me OY equal to 13,340. And then lastly, sum of the forces in the Z to 0. You got OZ, and that's going to be plus 0.6093 TAD plus 0.3965 TCE equals 0. Oh, I'm sorry, not equal 0, but have to also minus 8,000, right? Because we have that 8,000 in there, then that equals 0. So you have to count for the load that's applied. So we solve for that one and we get an Z equal to negative 2,560 pounds. All right, so that's then your 3 reactions and your tensions. So any questions on this before I make any comments more? Any questions on the process or anything? So as it may seem complicated the first time you look at it, but all these are pretty much the same no matter the shape. You notice that we started off 3-body diagram, identified our tension vectors, set up our moments to solve for the tension vectors. Once we did that, we then solve for our reaction here. And we can have it in different flavors, but it's still the same. High probability that a question like this would be on the midterm. So I would definitely understand it. I would also look at my past midterms. So my midterm for winter and fall, I would definitely look at those and look at how what type of problem I did for the 3D. It'll give you kind of an idea of the difficulty level that you'll see. And I think that's a good place to assess what to expect. Now, I recognize that you only have 50 minutes for the exam, and a problem like this could take that much time if I just threw it at you. So I may not always have you solve the entire problem, or what I might do is, since I know you understand how to get these values, I may just give them to you like I did on the quiz, the first quiz. Albeit I think there was an error in that, but never mind on that. But I'll give you these because these are, takes time to find these unit vectors, and I know you can do it. I don't want you wasting time on stuff. I want you to show me the new material and how you understand it. Okay. So any other questions on anything we've covered? Don't all speak at once. All right, well, that's good to hear. So maybe you're just in shock with how easy this class is and how trivial it is and how little you'll have to study in order to succeed. Maybe that's it. So I see that. So anyway, all right, well, that's all I have for today. So I do have office hours from 10 to noon. Tomorrow I won't, but I will reschedule them for Wednesday. Look for an announcement very shortly, early today, about what the quiz will cover on Wednesday and what the office hour time will be on Wednesday. And that's about it. And the new homework will be posted, but it won't be due until next Wednesday. So I'm not making the homework due Monday. I'm gonna have it due on Wednesday, since the test is next Wednesday. So I'll give you a couple extra days. All right, well, that's all I have. You guys have a good rest of your day, and I'll see you in office hours.
Thank you. I have a quick question.
Sure.
I'm one of the kids that did like the quiz 1 differently with the unit vector.
Yeah, I'm gonna go back and correct that. So yeah,
Okay.
yeah, I know. You're on my list. I know what you're talking about. Yeah. So if the unit vector was slightly off on the quiz for those you that hadn't heard that, and so if you did calculate your own unit vector, then I'll go ahead and correct it and give you the credit back. So I just haven't done it yet. But it's
Okay. Cool. Thank you. I'll just hang tight.
Yeah. Okay. Thank you.
All right. Bye.
Bye.